Yeah? Okay. We shall start. So welcome to my presentation, which has this long name, Enhanced Project Management for Embedded C++ Programming Using Software Components. Let me introduce myself. My name is Evgeny Druk. I'm a principal software engineer at ARM, and in particular in MCU Development Tools Department. As you can suggest from my sticker, I'm a developer, not in marketing. So I am a member of a team who is developing microcontroller development toolkit, also known as Microvision. And I do plenty of tasks for that tool, in particular the support for CMSIS-Packs. We will talk about what is that. And currently I'm also leading the development of the CMSIS-Pack support for Eclipse. And this is essentially what I'm presenting today. So in our talk, I will make some short introduction into the embedded software development challenges, introduce CMSIS and CMSIS-Pack specifications briefly, and then we will go to the main topic of today's presentation, which is the CMSIS-Pack Eclipse plugin, which implements the Pack specification, starting with the live demo, and then diving into the implementation details, such as architecture, runtime environment model, and promise it in the pitch slide, the CDT integration tricks. So let's start with the embedded software. So embedded software development was always different from the workstation mainframe development because you needed plenty of stuff. So you would need the device information, you would need startup code, device drivers, flash programming algorithms, device thing, debugger support, and so on. And as the modern microcontrollers becoming more and more complex, this information is more and more versatile, more complex, so your startup code grows. You need much more and more drivers, but you would like to concentrate on your application. And if you're designing something for the IoT, you would probably need an internet connection, so you would need a TCP/IP stack, for instance, so-called middleware. And you would even prefer to have some ready-to-use web application, so web server application, or Java machine running on your MCU. And you would like to have it available not only on a single particular device, but would be available for the range of devices. They are thousands nowadays, only ARM, only Cortex-M. There are also other MCU vendors. So, but how do you do that these middleware and application components run on many platforms, still able to talk with the low-level startup code and device drivers? So you obviously need unification and you need a standard. And we have such a standard, which is called CMSIS, the Cortex Microcontroller Software Interface Standard, which is vendor independent. You see plenty of partners who are participating in this standard. And this standard sets the foundation that enables to create and distribute reusable components. And to distribute the components, distribution is also a part of the CMSIS standard. And this is called the CMSIS-Pack specification. It's a delivery mechanism of software components and device information into a structured way. Technically, a CMSIS-Pack is a zip file which contains the source code, headers, documentation, examples, device information, plus XML description, so the pack description file, which in turn has several sections, the components, conditions, devices, and so on. So the component sections describe a set of software components. So any software component is defined by its taxonomy. So class, name, node name, class, group, subgroup, and variant, plus version of vendor. But if you have this such taxonomy, for instance, if you have a component with same class, group, and subgroup, it is supposed that another component with the same taxonomy shares the same API. That's the whole idea behind it. And the component itself consists of the files. So here in the description, we have the taxonomy in attributes and the list of files which represents the component. Components can depend on a hardware, so it should be supposed to run, for instance, on the STM platform, and they can depend on each other. And the conditions are intended to describe those two kind of dependencies, hardware and software dependencies. Software pack can also contain device descriptions in hierarchical way, from family, subfamily to the variant. And in each level, you can specify the device properties, the processor, which memory is there, how the debug support is done, and other features, including documentation, and so on. And it is done hierarchically, so you can save a lot of space, because you don't need to define for thousands of devices the same information for many times. Similar is for the boards, and you can optionally have examples in a pack which is either dedicated to a particular component or a particular board. One of the cool features of the CMSIS-Pack is the faster device support. When a device vendor produces a new device, it needs to bring it to market, but you can use a device only if you can program it. So, traditionally, device vendor, on the later stages of the development, contacts the tool vendors. As most of the programming is done by the third-party tools, not on the in-house development tool from the tool vendors. Supply the required information about the device and kindly asks the tool vendors to support this new device in the new release. And this could be time-consuming because the release schedule for the tool vendors is different from the silicon vendor. So you have to wait, and in the case you get some bugs in the specification, it could be take even longer before it comes to customer. With the CMSIS-Packs, it's much faster. So during the device development, the hardware development, the silicon vendor can already provide the required drivers, required startup code, pack its everything in the pack, test it internally, and then at the very same day they announce the new device, they can publish this pack, and the device support comes immediately. But this can be only true if at least most of the development tools support the CMSIS specification. Okay? That is why he has decided to push for the acceptance for the standard for the namely for this pack portion of the CMSIS standard, and provide a reference implementation for that. Open source with public license, so you can grab it, use it in your way, how you want. It's only published, so you can download this right now. Inside, it implements the basics, so how to access the pack information, how to create so-called runtime model to manage this information, and has the CDT integration, so it really allows you to create the project and build it. The plugin is primarily intended for the tool developer, so it's not an end-user plugin. You have to customize it. You need to provide the toolchain support, so binding, and most probably debugger, connection to the debugger, because the plugin itself doesn't provide the debugging support. So it's demo time. Yep.
I have a question. What do you think if silicon vendors will adapt this, like ST with their CubeMX and Frisco with their...
Yes, they are actually in the process. So I would say that Infineon, for instance, has already published their packs. So for ST, we have created in-house most of the support. By the way, ST is one of the most supported.
In general, they're okay with that. They're supporting.
Yeah.
That's only remotely related, but how does that compare to Yota?
So embed is a little first started earlier and targeted narrow market, much narrower. So they started with 2 devices. Currently they have a couple of hundreds. We are targeting thousands. So maybe someday we will have some synergies, but they established way of the distributing and developing software. So they are targeting a little bit different market.
It's more end user, and yours is more...
Yeah, and this is for... Okay, the demo. Here I am running our Development Studio 5 from ARM, but for us, for today, it's enough to know that it's Luna based. So the only feature which I use from DS5 is the ARM compiler toolchain integration. Everything else, what I'm demonstrating, is from this free plugin. So I've prepared some project, but I would start with the very new, the new one from the scratch. So as usual in Eclipse, you start a project with the new wizard. We have created a template, so based on the template engine, which is called CMSIS-OTEC++ project. So by the way, let me say it as a demo. We can select a compiler, but here are all compilers are listed here, even those which are not available for this project, to create such a project. This is done because the plugin is for developers, so they need to be able to test it even if the toolchain integration is not yet done. So, but for this particular ARM GCC compiler, we do have the toolchain integration, so it automatically detects that this is a GCC, and we do have that so-called toolchain adapter, a piece of software which sets the compiler options eventually. So for this small demo, I will use just a generic core, for instance, just an ARM. And so we have created a new CDT project. In order to, but it's still empty. First, what we need to add some basic components, starting from the startup, so device startup. It shows me that this startup depends on the CMSIS core component. So I either need to select this manually or let the runtime model to resolve it. I can also add some more components, for instance, RTOS and DSP, which are available even for the generic cores. And I can save this configuration. And as soon as I have saved, the project gets updated. So, and it copied all, it's inserted the required files into the project. There are two types of files. Some of those, mostly libraries, they are linked to the pack repository, and others are so-called config files. It's not enough just to select the component. In general case, you have to open this configuration file and edit it. Either assisted edit, just change some flags, or really write the code. So, but for this particular small example, we don't need it, so we will leave it as it is. The plugin also sets all the build settings. So, target processor, we have selected Cortex-M4 with little endian and with the floating point support. We do have preprocessor defines for it's a device define and includes. So similarly, we do have the libraries. Yeah, there for GCC they are listed as other objects because we need the absolute path to them. And we can try to build it. And it's done. So usually enormous applause comes here. That's the basic basic capabilities of this plugin. But I should mention one more thing. So the configuration file is a part of the project. So we essentially what we edit by selecting components, this file. It's just an XML. The project is dynamic, so you are not only able to add the components, you can also remove them. And the DSP library has disappeared. And as you see, there are component versions. You can either stick to particular or use latest. And if you install new packs, new latest packs, you need to update the project even by the loading it. We will talk about this later. That was the short demo. After the presentation, can show you some other features. Let's dive into the implementation. So I'm a developer. I would like to present what we've done. So I have said it's a plugin. In fact, there are 5 of them. The core one, which implements the most functionality. User interface, project, so CDT integration, build settings, and common stuff. These arrows show the dependencies. So as you can see, the core plugin depends only on a common, but has no dependencies on others and no dependency on Eclipse. So it's almost pure Java. Those, they really have dependencies to Eclipse, so to CDT or to the UI. But here, They also have some dependency between each other. If you look, the UI doesn't know about the project integration. It's the other way around, but this dashed line shows that it's not fully. So the project manager does use some common widgets and does use console, but has no idea about the configuration editor, which we have seen. So they are really decoupled. And the build settings is separated from the project management and depends only on CDT and the commands in order to provide the possibility to create the toolchain integrations. So if you need to create a toolchain integration, you only need this plugin plus command, and you don't need to install the rest. So it's very, very thin layer which you might need to use. As I said, most of the functionality is done by the core plugin. It itself has three areas. So the one which deals with the so-called raw pack data, so what it reads the packs and creates just a repository. Then the data references which we store in the project, so in the RTE configuration file. And the RTE model, which manages the information, so transfers one, so uses the both of these worlds. And let's dive into this particular plugin. So the pack data model is very much semantic free. So it's bare on its root. You've got the ICP item interface. It has actually 5 functions, 5 basic functions. Get tag, get text, get attribute to get the properties, and get parent and children for the hierarchy. Yeah, sure. For the convenience, there are some advanced functions, get URL, get pack, and so on. And derived interfaces, which describe pack, component, and device. Reference information has similar architecture, even more. The base interface extends this ICP item and also provides the information classes for the pack elements. And the RTE model, which manages both two worlds, have their own data types in similar way. But what is the RTE model? So the name is from the runtime because it manages the project dynamically when it loads or when it changes. The model filters the components, so for the particular device and selected toolchain, then combines them according to the taxonomy, so you can get the consistent tree here, manages the selection of the component through the controller, saves this information as the info reference data. It is also responsible for evaluating and resolving dependencies and resolving already saved data. Let's have a better look in the data flow. As you can see here, we have 2 distinct areas, fully symmetrical, project management and editing. Everything is done with the same interfaces or classes, but they are distinct instances of the classes. This is even the parser, which parses the configuration file and the installed packs, is essentially the same. What is different is the factories which produce the elements. So to add it to the project, we read the configuration file, so read the info, feed it to the model, which requests and collects all required information from the installed packs, and through the controller communicates to the GUI. As soon as we are done with the editing it, so all the bake saves to the configuration file. And the project manager just notices this and triggers almost the same processing, with the exception that we do not use any controller, but resolve the components and provide this information to two blocks, Toolchain adapter and the project updater, to update the project and the toolchain. Let's have a look in two of those. So, toolchain adapter. Why do we need an adapter? It's quite simple. Some compiler properties, like include path libraries or preprocessor, we can do in a generic way. And there are Eclipse plugins which allow that. But for the hardware, something like CPU type, you have to know the ID of the option. So actually the tool chain here is used in the terms of the managed build system. So that's not an executable which runs, that's the Eclipse integration of that executable. So we need to know this ID, and for some options we should be aware that, like linker script, that it could be generated. We also have to manage it. And any tool chain needs, therefore, an adapter. So even if it refers to very same compiler, you need to provide an adapter. It's done by the implementing this extension point and implementing the this RT toolchain adapter interface, or just extending the base class that gives you this portion for free. The plugin which is currently published has two fully functional adapters, one for the ARM compiler file and one for this cross-ARM GCC, which I have shown you in the demo, by the way. You can download this from here. This is third party, that's not done by ARM, but if you work with the GCC in Eclipse, I would highly recommend this toolchain. It's really very good done.
Do you know if IR is planning to provide these plugins?
IR, yes, they are already investigating. I have already the comments in the GitHub published, so they have questions, so they are on their way. I don't know about by their time frames. So, updating the project. Done asynchronously. When the configuration file has changed, we just load the project. This job is triggered. It copies, so it's not always copies. It updates the project files, deletes those which are no longer relevant. As I have said, there are two types of the files which are referred to or copied here. Then according to the CMSIS standard, it generates the RT components H file and updates the linker script or scatter file if needed. So usually only if you change the device. That's quite straightforward and nothing is fancy here. But one situation is tricky. And namely, when we just start Eclipse and load a workspace for the first time. What we need is to load C++ CDT project, then load RT configuration, update the project, and then let the index update work. Seem to be very simple. So Eclipse so CDT provides two listeners, one to postpone the indexer setup, one is to be notified when the CDT project gets loaded. And we even have the data provider extension point, which tells us when CDT plugin gets started. But that's still tricky because neither index manager nor description manager are available this time, so we can't register those listeners. So when the description gets loaded, namely description manager loads the data provider extension points, but still is not available. The singleton variable is not yet assigned. Then index manager is started and immediately scheduled. And this scheduler job asks if I should postpone it for some time or go straight away. And only after that, some time later, the loaded event gets fired. But we need to catch this event first and then let the index manager do the job. And the solution is to listen to this job to be scheduled. So it looks like this. We set register data providers as a setup hook, I have called this. It creates a job listener and listens when this job gets scheduled. At this point in time, we know that those two important members are already there, so we can register our listeners and then wait for the loaded event, update our RTE configuration, update the project, and then update the index. If someone has better solution for this, would be highly appreciated. That's the last slide in the presentation. After we have done build, we would probably need to do debugging. So we need to pass some information to the debugger. So the plugin doesn't provide debugging by itself, but it is intended to be integrated in the environment with the debugger. And the debugger would probably need, for sure would need, the device information, most of all. And maybe also information if some components are in use, for instance, RTOS. So do a runtime aware or not? Quite simple and straightforward. You just need an iProject. And everyone knows how to get iProject, I assume. Just for any selected resource or any application. And then you pass to the project manager, get the project, get its configuration, and you can query build settings, you can query the reference information from this reference information device info or directly from this configuration, and then gets its effective properties. So what is processor is used, what is the memory layout, which flash programming algorithms are available, and so on. And similar for the components. Okay, some conclusions. We have seen that CMSIS establishes a software, so it's a standard which allows us to create reusable components. It has specification to deliver these components to the tools, using the tools to the user. And the plugin, which I currently presented today, brings this functionality to Eclipse. And this is done to accelerate embedded software development. So that's it. Thank you. Some more additional links. So thank you. Questions, please. Yeah.